Hi, I'm Steven and I'm a tutor for Tutorfly. And today I'm going to be doing a review session for the upcoming AP Calculus BC exam. So we're going to do an overview of this review session. So the first thing we're going to talk about is the exam format. Then we're going to talk about key terms, formulas, and concepts that you need to know. And then we're going to talk about some tips and tricks to help you succeed. And lastly, we're going to go over some practice problems. So first we're going to talk about the exam format. So there are two main sections. So there's a multiple choice section and a free response section, and both of them make up 50% of your grade. So the first part of the multiple choice section is a no calculator multiple choice section. So you have 28 minutes and about an hour to do them. And afterwards you have a calculator section, which is 17 questions and also roughly an hour. And for the free response, there are also two sections. So the first section is a calculator section, and you have 30 minutes to do 2 problems. And the second part is 4 questions, and you have an hour to do it. So now we're going to go over important key terms, formulas, and concepts. So one of the main things you need to know about are integrals. So the one important formula that you need to know is the arc length formula. You also need to know improper integrals and how to calculate them using limits. You need to know, and you also need to know how to do integration by parts. The next concept we're going to talk about are differential equations. So the main technique, or the only technique you're going to use for differential equations, is separation of variables. And we also have initial value problems where you're given a differential equation and a value of your function at some point, and you have to use that to solve for your constant. And you also need to know how to use Euler's method to approximate your function. Next, we have polar curves. And you mostly just need to know the area bounded by the curve and the formula associated to it. So the next section is series. So you need to know your convergence tests and all the conditions you need to be able to use them. Then you need to know the error bounds for series. In particular, you should know the alternating series bound, because that one pops up the most on the exam. Then you need to know Taylor series. You need to know the formula for the coefficients. You should also know some common power series. For example, the geometric series and some common Taylor series, such as sine of x or e to the x. In this next section, we're going to talk about tips and tricks to help you succeed on the exam. So you should learn how to use a calculator effectively. So that means knowing any shortcuts and how to perform general functions on it. So you should be able to input quickly. You don't want to waste time figuring out where certain how to calculate an integral or derivative on your calculator, and finding zeros, since you need to solve for equations a lot of times. And the series convergence tests are really important, which is why I'm putting them here a second time. So the main tests you need to know are the ratio test, the root test, divergence test, integral test, and your comparison test, which are the direct comparison and limit comparison. In general, you always want to start out with the ratio test, and that one will be the most useful one most of the time. The next one that's really useful is the limit comparison test. And now we're going to go look at some practice problems. Okay, so we're going to start off with the multiple choice section, the section without a calculator. So for this first problem, we're going to figure out which of these series converge. So what we're going to do is we're just going to check each one. So for the first one, we're going to use the ratio test. So we're going to be using the ratio test to test the first series. So to use the ratio test, we just need to check this limit and make sure that it's less than 1. So after some calculation, you'll see that you have something over n plus 1, and this will always go to 0. And that's always less than 1. So you know that 1 converges. So for the next one, now we're going to look at the second series. And we're going to use the ratio test again. So again, we're going to calculate that same limit, but this time we're going to use this term instead. Alright, so I'm just going to cancel out the factorials. So I just get n plus 1 here. And then I'm going to write these two terms like this. So for this one will go to infinity, and this one goes to 1 to the 100th power. So then overall, this limit is infinity, and that's not less than 1, so that means that this series diverges. So now we can cross out B and E. And now we need to check the last series. For this one, you should see that when n is large, it behaves really similarly to n over n cubed, which is 1 over n squared. So instead of the ratio test, we're going to use the limit comparison test. So for our limit, the numerator is a polynomial of degree 2, and the denominator is also a polynomial of degree 2. So this limit converges to 1. And this is bigger than 0. So by the limit comparison test, since the series of this term converges, this one converges also. So that means that our final answer is going to be D. For this next problem, we need to determine the radius of convergence of this series. So the first thing to notice is that we can write the terms like this. And this means that this is actually a geometric series. And then geometric series converges whenever the absolute value of the inside is less than 1. So we have to figure out when this is true. So if we draw a picture of this interval, this is what we get. So the series converges on this interval, and then, so this entire interval has length 2 square root of 3, so the radius is going to be half of that, which is just square root of 3. So the answer for this one is C. For this problem, we need to approximate f of 2 using Euler's method with 2 steps of equal length, given that f of 1 is equal to 3, and the derivative satisfies this equation. So the first step is to draw a picture. So we're starting at 1, and our point is 3. Our height is 3. So what we're going to do is we're going to try to approximate f using tangent lines. So what we're going to do is we're going to find a tangent line to f, or to y at this point. So the slope is going to be given by dy dx at 1, 3, which is 1 minus 3, and that's equal to minus 2. So for our first step, this is our line. This is our tangent line, and we're gonna approximate, and we're gonna evaluate it at 3 over 2, which is halfway between 1 and 2. So the slope of this thing is minus 2, and then the change in x is 1/2. So that means that the change in y is gonna be 1/2 times minus 2, which is minus 1. So this means that this point is gonna be 3 over 2, comma 2. And then we do the same thing again. So now we have dy dx, but we evaluate it at 3 over 2, 2 instead. And that gives us minus 1/2. So this time the slope is going to be a little less steep. And we want to find out the change in y between 3/2 and 2 of this line. So using the same thing, the change in x is 1/2 again, and the slope is minus 1/2. So the change in y is going to be minus 1/4. So then this point right here, this is going to be 2 comma 2 minus 1/4, and that's going to be 7/4. So our approximation to f of 2 is 7 over 4. So our answer is going to be C. For this next problem, we're going to figure out which of these functions that this power series converges to. So for this problem, if you don't see it right away, it's best to just start writing down the power series for all of these. So for cosine x, the power series is given by this. And you can already see that the first terms don't match up. So this can't be the answer. For sine of x, we have x minus x cubed over 3 factorial, and you can already see that these terms don't match up either. So the next one is sine of x over x, and this is going to be 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, and so on. And you can see that these two series do match up. So the answer is going to be C. For this problem, we're given that this power series converges at 5, and we want to figure out which of the following are true. So this is a Taylor series centered at 3. And we know that a Taylor series converge, it always converges in an interval centered at 3 in this case. So let's draw a picture. And we know it converges at 5, so this means that it also converges at 1. Because 5 is 2 away from 3, and 1 is 2 away from 3. So we know that it has to converge on at least this interval. So the key thing to know here is that we don't know what happens at x equals 1. But we know that if x is anywhere in here, it does converge. And 2 is in here. So that means that the series also converges at 2. So the answer to this problem is D. For this problem, we need to calculate the slope of this polar curve at theta equals 0. So the first thing that's very important is that the slope is dy dx and not dr d theta. So to calculate this, we can think of this as a parametric equation. In polar coordinates, we can write y is equal to r sine of theta, and we know that r is this thing. Similarly, x is r cosine theta. And we know that what r is here too. So if we use the chain rule, you'll see that dy dx is going to be equal to dy d theta over dx d theta. So we want to calculate this when theta is equal to 0. So first, we'll calculate the derivatives. Since we want to find the slope when theta is equal to 0, all we need to do is substitute in 0 for theta in both of these. So dy by d. So that means that dy dx, when theta is 0, is going to be given by the quotient of these two. So we get 1/2. So the answer to this problem is B. For this problem, we want to figure out which values of p do both of these series converge. So we're going to start with the left one. So the left one is a p series, and we know that this series converges whenever p is bigger than 1. But instead we have 2p here, so we need 2p to be bigger than 1. So it will converge if p is bigger than 1/2. And for the next one, this is a geometric series, and that one will converge if p over 2 is less than 1. And that means that the absolute value of p has to be less than 2. So we draw this on an interval. So this is 0. So the geometric series will converge on this entire interval here, and the p series will converge whenever p is on this side. So overall, it will converge here. So our answer is going to be p is between 1/2 and 2. So it's C. So we're given the first couple derivatives of f at 3, and we want to figure out what the Taylor series of third degree for f at x equals 3 is. So the general term of a Taylor series is going to be given by this thing. So fn is the nth derivative of f at 3. So this means that our first term is going to be 2, and then our second term is going to be minus 1 times x minus 3. And then our next term is 6 over 2 factorial times x minus 3 squared. And our last term is going to be 12 over 3 factorial times x minus 3 cubed. And if we do some simplifications, we get this thing. And if we look at all the answer choices, E is the one that matches up. So for this problem, we're given that this series converges and all the terms are positive, and we want to figure out which of these are true. So the first one isn't true. These first three aren't true, and I'll use the same counterexample for all of them. So we can use a series. We can use this geometric series. And if you calculate this out, this is going to be 5 over 2 over 1 minus 1 half. And this is just going to be 5. And we calculate the limit of the ratio. It's just going to be 1 half. So first, this series converges and it's positive everywhere. And so A isn't true because then the limit of the ratio is 1 half and not 0. So we can already cross out A. And for this one, the first term is 5 over 2, and that's bigger than 1. So B is also false. For C, the sum is 5, which is not 0. So then it's false also. And for D, we're going to use this series instead. So this series converges because it's a P series and 3 is bigger than 1. But if we multiply the terms by n, then we get 1 over n squared. And this also still converges because it's a P series. So this is false. And that means that E has to be true. For this problem, we need to figure out the area of the shaded region, which is the circle and without the little petals here. So to find an area, what we can do is find the area of the entire circle and then subtract the area of these little petals here. So the outside is a circle with radius 2, so the area is going to be 4 pi. And then to find the area of the petals, we can just find the area of one of them and then multiply it by 3. So first we need to figure out our bounds for integration. And that's going to be whenever, we want to figure out whenever 2 cosine of 3 theta is equal to 0. And for this one, the values that we're interested in are going to be at minus pi over 6 and pi over 6. So when theta moves from minus pi over 6 to pi over 6, we trace the curve like that. And the area of this region is given by this formula. And that gives us the area for just one of these petals. So to get all 3 of them, we just need to multiply it by 3. So our total area is going to be 4 pi minus 3 over 2 times our integral. And if you put that in your calculator, you should get roughly 9.425. So our answer is D. So now we're going to move on to the free response. So a PDF to the problems that I'm doing will be provided, so you guys can follow along while I do them. So the first problem I'm doing is number 2. And what we have is that we have 2 polar curves, R and traced by F and G. So G is the outer one and F is the inner one. And we also have 2 regions. So R is the little pink region here, and S is the outer region here. And S does not include R. So the first part wants us to calculate the area of part of R. So we're just going to use the formula. So the area of R is going to be equal to this. If you put this in your calculator, you should get roughly 0.648. For this next problem, we need to write an equation which, when we solve, gives us a value of k that splits S into 2 equal regions. So to do this, we need to find k so that the integral, the area from 0 to k, is 1/2 of the entire area. In other words, if we multiply the area from 0 to k by 2, we should get this entire region. So the area from 0 to k is given by this integral. So what we're doing with this integral is we're calculating the area of the semicircle, and we subtract the area of R, and that gives us S. And then we want 2 times this to be equal to the area of the entire region. So the area of S is given by this. For this next problem, we need to figure out what W theta is. And W theta is the distance between the points F theta theta and G theta theta. So we need to find an expression for W theta and figure out its average value on this interval. So to find W theta, we need to find the length of this black chord here. So to do that, we need to take the entire length and then subtract the length here. So this entire length is G of theta, and this smaller length is F of theta. So W of theta is just going to be G of theta minus F of theta. And next, to calculate the average value, we just need to use the formula for average value. So this is equal to 1 over pi over 2 minus 0 times this integral. And if you put this in your calculator, you should get roughly 0.485. For the last part of this problem, we need to figure out what value of theta gives us W of theta equals WA. And then we need to figure out if W theta is increasing or decreasing there. So to solve this, you just need to use your calculator. And if you solve this equation, you should get roughly 0.518. And to figure out if W theta is increasing or decreasing, we have to take its derivative and evaluate it at this value of theta. So you can do all this on your calculator, and you should get the derivative evaluated at 0.518 is less than 0. And this means that W theta is decreasing. So this next problem is problem 4 in the free response. So in this problem, we're given that the temperature of something satisfies this differential equation, and that initially its temperature is 91 degrees Celsius. So for part A, we have to find a tangent line to h at t equals 0 and use that to approximate h at 3. So our tangent line is going to be able to form y equals mx plus b. And since it's a tangent line, we know that the slope has to be the derivative of h at 0. And we also know that y at 0 has to be equal to h of 0. But y of 0 is equal to b, so b is h of 0. So we already know b, and now we just have to figure out what m is. So we're given that h prime is this formula. So h prime of 0 is given by this. And we know h of 0 is equal to 91. And this gives you minus 16. So this means that our slope is going to be minus 16. So our tangent line is going to be equal to y equals minus 16t plus 91. And to approximate h at t equals 3, we just need to find the value of y at t equals 3. And that's 43 degrees Celsius is our estimate for h of 3. So for this problem, we need to use the fact that h is bigger than 27 also. So for this problem, we need to use the second derivative of h to determine if our estimate from part A was an underestimate or an overestimate. So first, we need to figure out what the second derivative of h is. So the second derivative is minus 1/4 times h prime. So h prime is this expression here. And we know that h is bigger than 27 for all values of t. So this means that this here has to be bigger than 0, and this is less than 0. So the first derivative is less than 0. So this means that since this is less than 0, and this is also less than 0, the second derivative is bigger than 0. So our function is, so h is concave up, so it looks something like this. And our estimate was using a tangent line. And the tangent line always stays below the curve, so this means that our estimate was an underestimate. So for the last part of this problem, we're going to use a different model for the temperature. So instead we're going to use this differential equation and g to model the internal temperature. So this problem wants us to find an expression for g of t. So we have to solve this differential equation. So to solve it, first we need to separate the variables. So I'm going to move all the terms with g to the left, and then move everything else to the right side. And then I need to integrate both sides. And this gives me so I'm writing 3c instead of c because I'm about to divide by 3 here, and I just want to be able to write c as my constant of integration. So now we're going to solve for g of t. And this is our expression for g of t, but we also have to solve for the constant of integration. So we're given that g of 0 is 91, so we just need to plug that in. So our constant of integration was 4. And now we want to, so our final expression for g of t is just going to be this. Now for the last part, we need to figure out what the temperature is at t equals 3. And that's just finding out what g of 3 is. So our final answer is going to be 54 degrees Celsius. So the next problem I'm doing is problem 5, and I'm just going to skip parts A and B. So for part C, we want to use the fact that f of x is equal to this to evaluate our integral. So by definition, this integral is going to be equal to the limit as t goes to infinity limit as t goes to infinity of 5 to t, and our function is going to be 2 over 2x minus 5 minus 1 over x minus 1. And then we just need to calculate whatever this integral is. So here, on the inside, these are both polynomials of degree 1. So this one, so the inside is going to converge to 2. So we get, as our final expression, natural log of 2 minus natural log of 5 over 4. And this means that this integral converges. So for the last part of this problem, we need to figure out if this series converges. So we're going to use the limit comparison test. So for when n is really big, this function is really similar to 1 over n squared. So that's what we're going to use for our limit comparison. So what I did between these two steps is that I divided the denominator by n squared. So this n squared goes away, and then I get a 1 over n here, and then 5 over n squared here. So if we look at this term goes to 0, and this term goes to 0. So this limit is equal to 2/3, and this is bigger than 0. So that means that since the series of these terms is converges, this series converges also. So the last response we're going to do is number 6. So we're given that we're given these properties of f, and we have to show that the first non-zero terms of the Maclaurin series for f are these, and then we have to figure out what the general term is. So the first thing we need to do is calculate the derivatives of f. So we already have the first derivative. So to calculate the second derivative, we have to take n equals 1 here. So this means that f double prime of 0 is equal to minus f prime of 0, and that's minus 1. And then for the third derivative, this time we're taking n equals 2. So we get that this is equal to minus 2 times f double prime of 0, which is minus 1, and we get 2. And we do the same thing again. This time n is 3, so we get minus 3 times 2, and this is equal to minus 6. And then next we just need to use the formula for the general term of a Maclaurin series. So the general term is given by fn of 0 over n factorial times x to the n. So f0 of 0 is just f of 0, which is 0. So the next term is going to be f prime is going to be when n is 1. So here we get 1 over 1 times x to the first power. And then for the second term, we get minus 1 over 2 factorial times x squared. And then we just do the same thing for the next terms. And we get this. And then you can start to see a pattern here. So the pattern is going to be when the denominator is whatever the power is. And this is also alternating. So we have minus 1 to the n plus 1, right? Because when n is 1, it's positive. Times x to the nth power over n. And this is our general term. For this next part, we need to see if the Maclaurin series for f converges at x equals 1 or not, and see if that convergence is absolute or just conditional. So from part A, from part A, we saw that the general term of the Maclaurin series is given by this. So the Maclaurin series is just the sum of these things. And we want to see if this converges at x equals 1. And that gives us this series to work with. So we can use the alternating series test to show that this does converge. So first we see that it is alternating because we have minus 1 to the n plus 1 here. And now we need to show that it's decreasing and that the limit of the terms is 0. So a of n, or the magnitude of the terms, have to be decreasing, and the limit has to be 0 for us to use the alternating series test. So the absolute value of an is 1 over n, and the absolute value of an plus 1 is 1 over n plus 1. And this is a bigger number than n, so this means that this is less than 1 over n, and this is equal to an. And that means that this is decreasing. And then next, this thing clearly goes to 0 because this is 1 over n, and when n gets really big, this gets small. So by the alternating series test, this series converges. So now we need to check if it converges absolutely. So now we want to look at the series of the absolute value. So this is the harmonic series, and it diverges. So at x equals 1, the Maclaurin series converges conditionally. So for this next part, we have to figure out the first 4 non-zero terms and the general term for the Maclaurin series of g of x, which is the integral from 0 to x of f of t dt. So to do this, we need to calculate the values of g's derivative at 0. So g of 0 is 0 because we get the integral from 0 to 0 of f of t. And g prime of 0, if we use the FTC, this is going to be equal to f of 0. And then if we take derivatives again, we get this pattern. That the nth derivative of g at 0 is equal to n minus 1 derivative of f at 0. So to find the general term of the Maclaurin series, we just need to use this formula. So when n is 0, g of 0 is 0, so it's just 0. For n equals 1, g prime is 0 is 0, so we get 0 again. For n equals 2, we get g double prime is 1 over 2 factorial, which is 1/2, times x squared. For n equals 3, we get g triple prime is equal to f double prime. So that's minus 1 over 3 factorial, which is 3 times 2 times x cubed. Then for n equals 4, we use the third derivative of f. So then that's 2 over 4 factorial times x to the 4th. And this is equal to 1 over 3. This is going to be equal to 1 over 4 times 3 times x to the 4th. And for n equals 5, we use the fourth derivative of f, which is minus 6 divided by 5 factorial times x to the 5th. And this is going to be equal to minus 1 over 20 x to the 5th. So our first 4 terms of the Maclaurin series are going to be x squared over 2 minus 1 over 3 times 2x cubed plus 1 over 4 times 3x to the 4th minus 1 over 20, which is 1 over 5 times 4 x to the 5th. And so then you can also see a pattern here because we can write 2 as 2 times 1. So the general term is going to be what x to the n, and whatever n is, we divide by n times n minus 1. So and this is also alternating. So we get minus 1 to the n plus 1 times x to the n over n times n minus 1. And this starts at n equals 2. For this last problem, we're given that p of n is 1/2 is the nth degree Taylor polynomial for g centered at 0, evaluated at 1/2. So we just want to show that the upper bound for the error at 1/2 for the fourth degree polynomial is less than 1 over 500. And we want to do that by using the alternating series bound. So this is the general term for the Taylor series for g centered at 0. The alternating series bound tells you that if you have a fourth degree polynomial, then the error bound is bounded above by the absolute value of the fifth term. So the fifth term of this one, the absolute value of the fifth term is going to be 1/2 to the n, or to the fifth power, divided by 5 times 4. And this is equal to 1 over 32 times 20, and this is 1 over 640. And this is going to be less than 1 over 500 because 640 is bigger than 500. So this means that the upper bound for this is going to be less than 1 over 640, and that's less than 1 over 500. So that's all I have for you today. Thanks again for watching, and if you want to learn more about Tutorfly, please visit our website.